Ladies and gentlemen, thanks for coming to this seminar. It is a pleasure to introduce our today's speaker, who is visiting from Norway. He's the Architect University of Norway. He is a visiting professor at UAA this academic year. So his name is Professor Eivind Brodal, who is an assistant professor at UiT, the Arctic University of Norway. He received MD in theoretical nuclear physics in 2003 from the University of Oslo. In 2008, he finished his PhD at UiT, where he investigated and modeled ultrasound systems. In 2009, he started teaching general thermodynamics and more specialized courses about heat pumps and refrigeration units at UiT. His main research interests now are to investigate advantages gained in cold regions like Tromsø and Anchorage, and to model, modify, optimize, and improve heat pumps and refrigeration processes using environmentally friendly refrigerants such as CO2. So today's topic of talk is refrigeration and compression processes in cold climates. Please welcome Dr. Eivind Brodal. Thank you.
Thank you. So today I'll talk about process advantages gained in the cold regions, optimization and modeling of processes. The cases I'll go into are from the oil and gas industry, the fishing industry, and I also will talk some about my research on heat pumps producing hot water and environmental friendly refrigerants. Norway and Alaska has much in common: oil and gas industry, fishing industry, and cold climate. And these are the topics I want to focus on in today's talk. Anchorage and Tromsø are actually sister cities since 1970. Tromsø is located very far north, almost 70 degrees north. And you see this map pointing at Tromsø and the equivalent in Alaska. So Tromsø is located very far north, but it's the temperature in the ocean and the climate is more similar to Anchorage, perhaps, than what it looks like there because of the Gulf Stream. There you can see actually how the Gulf Stream is melting a lot of the ice, or the ice isn't forming because of the Gulf Stream. So we have Oslo, which is about the same, about the same far north as Anchorage, and then you have Tromsø, which is on the other side of the polar circle, and then that's where UiT is, where I work. And we have a branch at Svalbard, which is almost 80 degrees north. So that's super far north. And there's a lot of international students going to this place. But also University of Tromsø has a lot of international students. And we have different courses taught in English. Actually, there's an agreement in the north, memorandum of understanding between UiT and UAA, established in 2015. And you can see reading here, Alaska's relationship with Norway is in particular important. If you go into our webpage, Process and Gas, where I belong, then you can see that we have two different study abroad programs for our students, and UAA is one of them. UiT is a major provider of Arctic science worldwide, and you can see here Tromsø, University of Tromsø is among the 10. We publish among the 10 biggest institutions publishing articles for the article about the Arctic. UAA is almost leading. Research focus at UiT is health, welfare, quality of life. This is from our homepage. Technology, sustainable use of resources, energy, climate, society, environment, Arctic. So you can see the focus at UiT is strongly related to the climate. And what is the future for oil and gas in Norway now? That's a big debate in Norway. The future is in the north because all the oil and gas fields are, much of it in the south is already explored. So the oil industry is moving north, and there's still significant opportunities in Norway for oil and gas. But then people are saying, why should we drill more? And maybe oil and gas, hydrocarbons isn't the future because of the global warming. And actually, what we experienced is that oil and gas studies in Norway has attracted much fewer students in recent years. So, for example, this is from our homepage, Process and Gas Technology. And we are actually considering changing the study program to attract more students, maybe focusing more on general processes, not hydrocarbons. Norwegians trust their elected politicians, even the ones they didn't vote for. And I think one of the main reasons for that is that politicians in Norway can't ignore science. There's actually very few people in Norway complaining when we had to lock down because of coronavirus, and people listen to the scientists, and the politicians listen to the scientists, and then people believe that the politicians are doing the best. So some fun facts. Much of the income from oil and gas has been saved in Norway. Norwegian government have now saved $200,000 US per person. The Norwegian Oil Fund owns 1.4% of all the stocks in the world. And people in Norway are happy with that. So I think even the rich and the poor agree on this. So if you ask a person working at the gas station, they most likely say, if you say, do you want $200,000 US tomorrow on your bank account? They would say no. They believe it's better for to have the government dealing with this money. In March and April, we had very strict lockdowns. Tromsø population, 75,000 people, have had 20 cases of COVID during the last 120 days. In school, they opened in May, in the beginning of May. And things are I think things are more normal in Norway than Alaska right now. Anchorage has about 4 times the population as Tromsø, so that would be equivalent to 80 cases. And that's what we experienced here yesterday, I think, almost. I think I'm happy with what the government did in Norway, locking down hard, because it seems like it's much easier to keep the numbers down when you have a few cases. If you have to find the contacts of 20 people and ask them to isolate for 10 days, it's much easier than if you have 3,000 people that have had COVID and you need to find their contacts. The government is trying to fight global warming. For example, they're giving electric cars economic advantages. Actually, now more than 50% of the new cars sold in Norway are electric. Also, the government is supporting CO2 capture and storage technologies. And they also regulate the refrigerant industry. So here's a table showing that in Norway, I think it's the only country, but where we have a deposit on HFC refrigerants, because they cause is a major contributor to global warming. And in Norway, if you buy R404A, which is a common refrigerant, maybe it costs $1 to produce it, maybe a little bit more. But then when you buy it, you have to pay $200 extra per kilo. So the deposit is huge, but that's because the industry, you had to regulate the industry this way. The politicians thought, but they asked scientists, what should we do? The deposits are given back when the refrigerants are returned. This has caused much less leakage. It's much cheaper to call a person in to repair than having a leakage to the atmosphere. And also environmental friendly refrigerants has gained popularity. And this has contributed to that Norway is now one of the leading nations on environmental heat pump technology. So here you can see the deposit introduced in 2004. Before that, we had an exponential increase of HFCs in Norway. But after that, it kind of stopped, and now it's on a downward trend. But it's not just Norway working on this. There's agreement. Developing countries have a little bit longer time to reduce the use of these chemicals. Industrial countries have to do it faster. And you see in the chart to the right that the EU is doing a little bit better than US, and Norway is doing a little bit better than EU. So I want to say something about the refrigerants, the past and the future. The first refrigerants, they were natural refrigerants. That is refrigerant chemicals that are already in the nature, like CO2, ammonia, and propane. This refrigerant had their problems. CO2 had to work on high pressure and were not very efficient in warm climates for refrigeration. Ammonia is poisonous and have other issues. Propane is explosive and can easily burn. So when the chemists came up with synthetic molecules that didn't have these unwanted properties, they became popular, and people stopped using the natural refrigerants. But then later on, they found out that these new synthetic molecules had unexpected problems. So they were bad for the ozone layers, and in the 80s, the world managed to get rid of those. And it went kind of smoothly because the refrigerant, the industry that produced synthetic refrigerants, they could switch to making new other synthetical refrigerants, the HFCs, and the ozone layer was saved. But now the problem is that these new synthetic chemicals, they are a major contribution to global warming. So where we are right now is at this, where are we going to go in the future? So the industry could easily go to this HFOs, which are new chemicals, not natural, and with the properties that are advantages, like locally, but we don't know what maybe there's going to be a problem in the future again. We had 2 times now introduced new molecules to the atmosphere and experienced problems. So in Norway now, the most scientists think that we should go back to where we started with the natural refrigerants. In Tromsø, a company, there's a company who gained much attention for CO2-based refrigeration in fishing vessels. You can see here is a picture of the SuperFreeze model. And the SuperFreeze model is a little bit different than the other already existing models because it operates with a much lower temperatures. And that can reduce the freezing time with 50%, lowering cost. And also, when you freeze the products down very fast, you can argue that the product is better. But you can do that because you use CO2. CO2 can be very cold and still be above the atmospheric pressure. And also, it's not a hazard, you could cool down the fish directly with CO2, so you don't have to have an indirect refrigeration system, or will reduce the COP. This company also deliver RSV, where you cool down seawater together with the fish. And it was the first to deliver CO2-based RSV units on a boat in the world, and that was done in 2010. So this is kind of a new technology. So going into the research questions and findings, we studied a lot about the ambient temperature. So this map shows the temperature, the sea surface temperature around the world. And Melkøya is shown, that's close to Tromsø and has LNG industry. So you see that the temperature in Tromsø, around 6 degrees, is similar to the temperature in Anchorage. Cold regions are often related to additional costs because of icing, the remoteness, and there's small populations, so you have to fly in people if you can operate there. But can cold climate also be advantage, reducing cost and CO2 emissions? That's a question I've been very interested in, because some processes needs less energy in cold climates, in particular processes using compression or refrigeration. For example, LNG, liquefied natural gas. The product is natural gas at minus 162 degrees and atmospheric pressure. But it's kind of obvious that if you start from 5 degrees, when you cool down, you save energy than if you had to start from a warm location, for example, 25. But also there's other more hidden benefits. Indirectly, because the refrigeration process is more efficient, because there's compressors in the compression cycles, and if you're able to cool down the temperature before it enters the compressors using ambient temperature, then you save energy. Production of liquefied hydrogen is similar to the LNG. You cool something down really to really low temperatures, so you probably save similar percentage with cooling down hydrogen. CCS, carbon capture and storage, a main thing that costs energy is the compression to a high pressure. So you could you need to compress the CO2 before you in the transportation, and that includes a lot of compressors. And so if you can cool down the temperature before each stage, you save a lot of energy. Also, power plants can be more energy efficient, such as gas and steam turbines. You probably remember the Carnot cycle, operating between two different temperatures, a max and a minimum. And the minimum temperature is related to the ambient temperature. So if you lower the ambient temperature, the efficiency of the increase. So what are optimal processes in cold regions? How can systems be made more friendly for the environment? So this is a picture of the continental shelf in Norway. You see Tromsø, UiT, and Melkøya nearby, and you see how the oil and gas is explored. So the industry is moving here. The LNG plant at Melkøya is claimed to be the most energy efficient in the world. One of the reasons for that is maybe its location very far north. But still, it's responsible for 2% of the land-based CO2 emissions in Norway. So it will be nice to reduce emission from LNG plants. The results, if I have time, I'll talk about the model a little bit later, but the results shows that Melkøya is done as a base case here, so it's 0%, and then it shows that Middle East, the energy usage is around 20% more if you want to cool down, produce LNG, so the cooling process. So that's quite significant. And since LNG plants, they always burn natural gas to produce the electric power needed in refrigeration. So the percentage saved in energy is directly translated to the CO2 emissions saved or reduced. So that means you can reduce the CO2 emission by building LNG plants in the north. So is it better for the global environment to build LNG units in the cold climates? If Melkøya plant was built in the Middle East, the world total CO2 emission would increase with about 0.5% of the Norwegian land-based CO2 emissions. However, building LNG plants in the north doesn't solve the global warming problem because the LNG is burned later on and releasing about the same amount of CO2 as the whole of Norway. So carbon capture and storage could be a solution to this problem. You have the oil and gas, you send it to the power plants, you catch the CO2, and then you transport it down into the ground where it is stored. And if you look at the compression, the transportation process, the energy usage, you see that Melkøya is around 12% less energy to do CCS in Melkøya than in the Middle East. And you can see Anchorage is about the same temperature as Tromsø, so it's about 12% less energy than in the Gulf. So is it better for the global environment and economically to carbon capture in cold climates? Is the question. And we studied this in this article. The carbon capture can be done in different processes. You need a lot of compression stages, and then you have refrigeration and pumping. It's an alternative way of getting to the. You typically start in this article. We assumed 1 bar in the beginning, and then the discharge pressure was set to 150 bar. So you could either just do compression, different compression stages like in the figure, or you could do some compression, get above the triple point of CO2, and then cool it down, and then just use a pump when the CO2 is a liquid. So this compares systems of different at different locations. It's very important to optimize the system for that ambient temperature. So in this study, we saw that you need a different number of compression stages at different ambient temperature. Because you have to compare the optimal under the same basis. And when this was done, our results show that the energy uses at different places is given in this map, and then you can do the so you can save a lot, and that's what I showed in this figure I showed earlier already. That there's a percent-wise there's an interesting gain. So what is the future for oil and gas in Norway? Both climate leader and oil giant. Oil and gas are vital to Norwegian economy. And this article said Norway says its new giant oil field is good for the planet. I think they meant that because they had a lower CO2 emission in the production. But still, the hydrocarbons are eventually burned and releasing CO2 to the atmosphere. So an interesting thing we looked at is how can the hydrocarbons be exploited with a neutral CO2 footprint using the CCS schemes, and what is the best way of doing this. And I have a PhD student in Norway who looks into this, which scheme is best, how should you do the carbon capture. One way is to produce LNG locally and export it like we're doing today in Melkøya to consumers, which burn it. The consumers today probably don't capture the CO2, but in the future they could. So that's one alternative. Another one is to burn the natural gas locally. So you burn it, you have a gas here instead of the LNG unit, you have a power plant, and then you capture the CO2 and put it back into the ground where the natural gas came from, and then you export the electric power. But then the Arctic in the north, that's remote places, so then the power grid, the electric power has to be sent quite a big distance through the power grid, so there's be losses with that. But then you save the energy used on the LNG production by cooling the hydrocarbons down, and also the power plant might have a little bit more better efficient in the cold climates. So you could put all these small details together and try and figure out which way is most energy efficient. Another alternative is that you make hydrogen locally from the natural gas. You capture the CO2 released in that process, and you export hydrogen. So which of these three cases, all carbon neutral processes, which one is best? And that's what my PhD student is looking into. CO2-based units for fishing industry. I've been working with that. And this is an article talking about this, RSV units, refrigerated seawater tanks, where you put the fish. CO2 refrigeration units are efficient in cold climates, but inefficient in warm climates. So why is that? The reason for this is CO2, 30 degrees is around the critical point. So around that temperature, the CO2 becomes inefficient. And the reason is that when ambient temperature increase, then the compression power increase relative to the refrigeration duty, and then you get the lower COP, coefficient of performance, which tells how efficient the refrigeration is. And if the temperature increased even more, you have to go transcritical, and the COP is even worse. So this is what was modeled in this article. You have the compressors, gas cooler if it's operating transcritical, and this is a condenser if it's subcritical. And then you have a receiver, expansion valve, and evaporator. And then you have a big RSV tank, which is cooled down. When modeling this, we used factory compressor performance data. So this shows the isentropic efficiency of the compressor and the volumetric efficiency of different discharge pressures and evaporating temperatures. We also included a heat exchanger model from HYSYS, which was run each time in modeling. So this was more specific with the dimension and stuff. So results shows the COP, coefficient of performance, this unit achieved, because the tank always started at the seawater temperature, not below. You get this triangular graph. And about 20 degrees, the system with this exchanger used we had to go transcritical. It was more efficient to do that. So, and then this COP data was put together with temperature data around the world, and shows that in the north, around Tromsø, the COP is around 5, which is similar to Anchorage, which is very good for a refrigeration unit. Before the company in Tromsø started making CO2-based RSV units, ammonia was the most popular one in Norway. It might still be the most popular one. It's also maybe gets better COP than CO2, but it has other issues. So CO2 has gained a lot of popularity. So CO2 is more efficient than the conventional R22. If this in cold climate around 10 degrees. So you see in Anchorage, CO2 is maybe more energy efficient, and also if you have a leakage, it's not it has a low GWP compared with other refrigerants. So here are some scenarios we modeled. There's some different regulations you have to follow, like the fish has to be cooled down to 3 degrees before 6 hours, and has to be 0 degrees after 16 hours. And then they model different seawater temperatures and how the tank was filled starting before you started fishing, cooling down parts of the tank. And then we looked at COP over time. We also looked at heat pumps for tap water heating. CO2 has been known for more than 2 decades to be very energy efficient in cold climates for tap water heating. But we looked at a relatively new modification combining space and tap water heating. So this is shown here. We have a compressor, so this is CO2 going in the system, internal heat exchanger, and then evaporator. So this modification is to introduce space heating. And the space heating, that's if you have a floor heating in a building, that typically doesn't have to be that warm, maybe 35 degrees, because the area or the floor is huge. So you can have a so you have a large heat exchanger into the room, so you can maybe have 35 degrees Celsius water heating that. But the tap water, you have to warm up higher, maybe to 70 degrees. And this system we actually have in a lab at the UIT. So this modification with space heating increases COP, or can do it, because it reduces the heat exchanger loss. So what you see here is the CO2 being cooled down in the 3 different exchangers showing here. So in the first exchanger, CO2 warms water to 70 degrees. So you can't cross, it's impossible to cross this, have a temperature crossing here. The heat is always going from the warm fluid to the cold. And then you have the second heat exchanger, space heating, warming water from 30 degrees to 35. And you see there's a very good match here, and that's why you increase COP. And then you have the last heat exchanger here, warming the water from the ambient temperature up to 25 in this case. So you get less thermodynamic loss in heat exchanger because you have a very good match between the temperature profile of the refrigerant and the heating demand. And this is a heat temperature diagram. So the area between the graphs, they show how much entropy you generate. And if you have a good match, then you create little entropy, and then you have a energy efficient process. So you have on this side, you have tap water heating, pure tap water heating, and you see This is CO2, and then you have different cases with the ejector and without the ejector, and then also looked at some other cases where you just have 2 heat exchangers. But you see in all cases, introducing this gas cooler for space heating increases COP. But we also see that it has a much higher COP for pure tap water heating than pure space heating. And but you also see that maybe you have a 10% gain if you had this. So you gain 10% energy efficiency if you have this, if you can use some heat to warm the space in the house. We also compare the system with a conventional system with R410A. And what we saw then is that for tap water heating, CO2 was much better than R410 if the temperature was cold. At 30 degrees, R410A was better. So cold climate, CO2 was better than the conventional system. But for tap water heating on the side, you see that R410A is always better. So we also studied blends. If you mix CO2 with propane, that's what we investigated. What kind of gains do you have? So we modeled heat pumps with a suction gas, heat exchanger, ejector, and CO2 propane blends mixes. We looked at these different systems. And so this is pure propane for this system with an internal heat exchanger. So then you have 3 different heat exchangers. You have the gas cooler, you have the suction gas heat exchanger, and then you have the evaporator. So you have the 3 different, so this is a condenser, this is the internal heat exchanger, and this is the evaporator. So for propane, you see there's not a good match between propane and the tap water, the heating demand. It's tap water heating up to 70 degrees. So this is not very efficient. If you look at CO2, the difference is much less. The average is 12 instead of 19 degrees. So this CO2 therefore have a better COP than propane. But if you add 10% propane to CO2, then you get the even better match between the heat exchanger. You can also see in the evaporator, you also gain, you reduce the temperature difference in the exchangers. So then it's possible to have a more energy efficient system. Yeah, so here the COP is calculated for different mass fractions. So this is pure CO2 and this is pure propane. So you see for CO2 system, adding having an ejector in the system, you increase the COP significantly. But you can almost get the same gain if you don't use an ejector, but you use a blend. You blend in some propane, like 20% propane. And this is a different case with a higher ambient temperature. And then you see that the CO2 is not the best alternative. With the ejector, it's a little bit better than pure propane. But the best system is these systems where you have most propane, but some CO2 blended in. And then I mentioned the LNG process, the model we had related to the article I showed earlier. So the model, optimization, and results. So this is the article. And it's discussing the mixed fluid cascade, which is the process we have at Melkøya. It's kind of a complicated process. It uses 3 different refrigerant blends, and each blend has 3 different components. So some natural gas is entering here and being cooled down to maybe minus 40, maybe minus 100, and minus 162. So you do it in stages. And this is the first refrigerant blend cycle. And this is much propane in this cycle, and heavier hydrocarbons, and it gets lighter when the temperature, you have to cool down further. So the process is modeled in HYSYS. Compressors are modeled using isentropic efficiencies. Heat exchangers are modeled with minimum temperature pinches and different constraints. Yeah, so there's a lot of different constraints, minimum pressure, compressor pressure ratio, minimum superheating, and so on. Optimal operating parameters are found for all ambient temperatures. So then it's important to optimize the system for each temperature, because what is good in a warm climate is not good in a cold climate. And here you see the different, the most optimal refrigerant composition of the first mixed refrigerant. And the different processes studied, yeah, so you had to have different optimization variables going all the way up to 18 different things that were optimized at each temperature, plus all the constraints. So it was a difficult problem to solve for the computer. The results show that the MFC process is the different processes gain about the same amount of energy by operating in cold climates. Yeah, the results show that yeah, 20 to 26% higher in Middle East than in Arctic climate. And then we use this to combine with seawater temperature around the world and get this map I showed earlier. Then again, you see that the temp in Anchorage, which is same as Melkøya, so it's 0. Then you gain 20%, or you use 20% less energy in Alaska than in the Gulf. So yeah, so it's interesting to see what can be gained in the Arctic climates. Also with respect to global warming. Yeah, that was what I had to present today.
All right, thank you very much. That was awesome. Yeah, very, very interesting. And so I think most of our, oh, okay. Yes, what software, sorry. So moving on to the Q&A, we already have some questions coming up here for you. The first one is, what software is used for modeling?
Yeah, the software, so LNG articles, I use HYSYS, which is developed by the oil industry. So it's, but for the heat pumps, I use, so I work in MATLAB, and then I use CoolProp or Trend. So for mixes and Trend is good, and but also CoolProp is good, good to get the refrigeration. Yeah, to find the properties of refrigerants.
Awesome.
And sea surface temperature data I got from Japan Meteorological Institute. They have good data on the temperature around the world.
Awesome. All right, so I've got a general interest question for you. Like, what temperature do you usually keep your houses at there? Because in Anchorage, like 68 to 72 degrees Fahrenheit, which is close to like 20 to 22 degrees Celsius, is common. So what temperatures do you usually have there indoors?
I think it's about the same. So in Norway, before, when I grew up, people didn't care so much about electric power usage, because we had the hydro power, and the electric power was much cheaper than elsewhere on the continent. But now, after the global warming issue, and so now people are trying to save, and there's like nobody's heating their. I don't think it's allowed to like melt the ice from your driveway, and I don't think people have heated garages and stuff like that in Norway. So but I think the temperature in the houses are similar to what we have here.
Okay. And so let's see, what other questions? Trying to find some questions online, but it doesn't look like we have too many online right now. So you had mentioned that you're leaders in heat pump technology. The question I had was, what have you learned about heat pump technology that others haven't yet? If you can give us a hint.
It's basically just natural refrigerants. It's interesting to go back to those that don't lead to global warming if they're leaking out to the atmosphere. So yeah, so yeah, it's yeah, I don't know what more what to say. It's yeah, what was the question again?
Oh, just kind of, since you're the leaders in heat pump technology,
Yeah.
what have you found out? What are you kind of looking at now that other people haven't yet looked at?
Yeah, so now it's just like small steps, and it's yeah, like the Tromsø company was the first to build CO2-based RSV units and superfreeze units they have, and also like the fishing industry. I think maybe it's a big yeah. Norway's not using so much global warming refrigerants as many other places. And that's probably because of the strict regulations. So people have been forced into using those natural refrigerants earlier than other places.
Okay, awesome. Well, I'm not seeing any other questions come up. The password for today's survey is cold, for those of you completing the survey online. And I thank you very much for taking the time today to talk to us about this very interesting topic. And thank you for all of your hard work in this research.
Thank you.
All right.